Okay, last time we actually try to find the electric field from a surface charge, right? Remember, it's just yesterday. Okay, and we know that the electric field from the surface charge is this one. Right, because we have a surface charge like that, and we have it charge density is sigma. Okay, and we use the Gauss surface like this. It's the pill box. With the area of A. This is what we use. And as a result, we have this as a solution. Okay, and actually comment about the radius or the distance independence, as I told you that this E here does not depend on R, right? It is independent of how far away you are. It doesn't matter. It's always equal to this one. And I actually tell you the reason, right? I told you the reason that let's consider at this point, right? This one is R here. So there's not only a charge here that contribute the electric field to this point. There are also other places, right? This one also contribute to this point. This one also contribute to this point. So there are many other, charges allowed that contribute the electric field, on this location, on let's say P here, on P. This is only true. It's only true for what? For infinite surface. Okay, only valid for infinite surface. What do I mean? I mean this surface is actually extend to infinity. Okay, it's really broad, very wide surface. Okay, this is the condition. If your surface is not infinite surface, what I just said is not true. Okay. Okay, now we're going to try another example that, using this concept. Okay, now let's look at another example. Okay, we have two infinite. See, it's really important. You have to say that infinite parallel planes, and they both carry equal but different, no, you can say but opposite uniform charge density plus and minus sigma. Okay. Okay, what do we want to know here? We want to know the E field, electric field in 3 regions. Okay, let me draw a picture so you can see it better. Let's say we have a parallel plate here. It's one of the plate here, and I have another one here. Okay, let me draw with different color here. Okay, we have a parallel plate that, and they are extended to infinity. It's infinity surface. Okay, and one of them is positive. Let's say this one is positive here, and this one is negative. And we want to know within 3 regions. It means this region, 1 here, 2 here, and 3 here. Okay, these are the regions that we want to know how much is the electric field there. Okay, so how are we going to do this? First, let's consider only one plate. Let's consider only the red one. Yeah? We consider only the red one. Okay, the red one has the positive charge here. So the electric field from the lead is going this way, right? Going both sides. Okay, let's put it as a B plus here. Okay, I only draw one line. There are other line also. There's also another line here, and E plus here. Okay, this is the electric field from the positive charges. Okay, the positive charge density, and this E actually going all the way equal. It can go anywhere, right? Because it doesn't depend. This E is independent of R, right? So E here and E here, they are equal. Okay, this is the positive. Okay, on the other side as well here. Okay, now let's consider the blue one. Okay, the blue one here. That's so beautiful. Okay, and this is negative here. And there's another chart, right? N is going this way. This is our N here, and this also our N for this. Okay, and for the negative chart plane, the unit vector is also perpendicular to the surface and pointing out, okay, not pointing in. That you have to be careful. So if you remember, our E field for this is this one here. All right, and if you have a negative charge here, you can say that it's this one here. All right, is that clear? So in this case, the field of the negative surface charge going the other way around. So it's going this way. Okay, let me use the blue one here. Okay, and the other side as well. And it's also going anywhere, right? And this one also. Okay, I only draw one line. It's okay, right? You understand it. Now we put them together. Okay, now we put them together. Let me copy this. Okay, now we put them together. What happened? Can you tell me? Can you tell me what happened? Okay, let's draw it. Okay, for the positive one, E field is going this way. Okay. And the negative is going the other way. Okay. Okay, I draw it. No one tell me that this one is not correct. Yes.
Yes. Yeah. The direction from the minute chart is not correct. Right?
Yeah, it's not correct. It should go this way.
The left picture.
Oh, sorry. It's going the other way. Thank you. Okay. It's going this way. It's going, toward the plate. Okay. It's going toward this plate. Okay. Let me draw a simplified version so you can see it better. Let me draw only a line here. Okay, and another line here. Okay, so this thing is positive and this thing is negative. Okay, so drawing like this is a little bit easier. So I put like that. It's E plus, right? And this thing is E plus, and E plus also going the other way. And for the negative chart here, it's okay. If you look, on the side, you have this. So this thing is the first region, second region, and the third region. Oh, sorry. Can you still see me now?
Yes.
Can you still see the page?
Yes.
That I show? Okay, good. So what are we going to do here? Can you tell me what is the first region? What is the electric field in the first region? On the first region, yeah. What happened to the E field here? Are we going to have a charge outside in the first region? Do we have an electric field here in this region? Are we going to have it? Okay, now we are considering this region. You can see that E field here is pointing this way, the other one is pointing the other way. So the summation of them is what? Is 0, right? So in the first region, E field is 0. There's nothing there because it's cancelled out. Okay. Any questions? And how about in this region? They are also cancelled each other out. Okay. We only have the electric field inside here. So the first region and the third region is completely no electric field. Okay, but in the middle, in the region number 2 here, you can see that E field here and E field here, they point toward the same direction. Okay. Okay, they point toward the same direction. So E field here in the third region, E field is what? It's the E divided by 2. Sorry. Okay. So do we have?
That is for the second region, right?
Yes, it's for the second region. Sorry. Thank you. So they just sum up. They point into the same direction. Okay. So this is the E field in this region. Thank you. Okay, in this region. So what actually this example inform us? It actually tell us that if you have a parallel plate, if you have a set of a parallel plate here like that, so you have a positive and you have a negative, the electric field inside will go this way, and there's nothing else outside. You don't have to worry about it. Okay, it's good for, you know, we will going to study the capacitor. Okay, the capacitor. Okay, and the capacitor, the simplest form of capacitor is a parallel plate system, and which is this one here. Okay, we will talk about the capacitor later. Don't worry, we will see it later. Okay, now we are actually ready to do some simple homework. It's going to be more homework coming. Okay. Okay, it's 2.12. 15. Okay, I didn't write number 2 here. Just to, okay, let me like so you clearly understand it. 2.15. 16. 17. Okay. I think we will need to find times to actually spend on the homework. You know, we will have a problem session so that, you know, I can show you some show you the solution of some of the homeworks, and you can show me the solutions of, you know, the one that I didn't show you. Okay, we will need to find time, maybe on Saturday or Sunday if you want to, because this class you need to do some exercise with the problems, otherwise you will not understand it. Okay, we will talk about it later. Okay, next we have done the divergence of electric field. Now we come back to curl of electric field. Okay, let me line in. Okay, now it's curl of E. Okay, we can do, well, we can follow the same concept as we did for the divergence. Okay, we find for the divergence, we consider the flux of the electric field. But in this case, we know that for the curl here, we can consider the integral of E dl. Okay, the integral of E dl. Why do I consider this? Because we know that from the Stokes theorem, curl E here, dA equal to E dl. Remember? Can you recall that? We talked about it before. Okay, so let's consider this. So it's the simple one. Instead of doing this, it's a little bit more difficult. We do this, okay? And we can consider the closed line integral later, okay? Okay, for E, for the simplest form of electric field here, E is equal to 1 over 4 pi epsilon naught Q divided by R square R, right? This is the simplest form of electric field. Is the electric field from a point charge Q. Okay. Any questions? So we want to find the line integral of this E field here. We want to find the line integral of this E field here, the line integral here, of this E field from A to B here. Okay. We want to find a line integral. So how can we do it? Let's say that, okay, we consider the general form in spherical coordinate. So it's more difficult. Let's consider dl here in spherical coordinate. We actually learned it already, right? We talked about this relation before. Okay, this is our dl here. So the line integral of E field here, A to B here. Because our E field here is only in R direction, so we will have this. Any questions? So our indication from A to B here. So what do we have? We have 1 over 4 pi epsilon naught Q here. 1 over R A minus 1 over R B. This is the result of the integration. Okay, you can think of it like that, like this. Let me draw a picture for you. Okay. You can say that this thing is point A here. You can say this RA. And okay, this can be B here. This thing is RB. All right. Any questions? Any questions? Okay. When we thinking about the closed loop here, what do you mean by closed loop? It means that you going this way and you coming the same place, coming back to the same place. What do you think this thing will give as a result? So the point A going to B here and B coming back to A. What is the result of this line integration? Can you tell me? Anyone can tell me what is the result of this line integral? So you're going from A here, right? Going and coming back to A. What does this mean? It means that RA and RB are equal. Closed loop. So RA equal to RB. Otherwise, the loop, the line is not a closed loop. Okay? If you're going this way and you stop there, it's not a closed loop. It had to come back to the same point, to the same, to the initial point that you begin to move. Okay, that you begin to, consider. Let's say you consider point A here, going to here. If you stop here, it's not a closed loop. If you're coming back to A again, yes, it is a closed loop. Is that clear? So RA here equal to RB. Okay, RB. Or you can say that from A here to A, back again, the same point. Any questions? No? So what is the result of this? It's 0 here. Are you guys still there? Or gone?
Still there.
Okay. Is it clear? Is it clear here?
Yes.
Okay. Now, since this thing is equal to 0, we come back to Stokes theorem. This one is Stokes theorem, right? I forgot to tell you here that is Stokes theorem. And I believe that you know it if you go back to study. Okay, since this thing is 0 and from the Stokes theorem, we have this curl of E field here, dot dA here, equal to closed loop E dot dL here, right? So since this thing is 0, of course, curl E must be 0. Okay, it's 0. Is that weird? What this tell you here? What does this equation tell you? It tell you that E field here for the static case is going outward, not coming back. Okay, it's going outward. Let's say you have a point charge here. It's going this way, all direction, but it's not doing, it's not going this, it's not doing this, it's not coming back. Okay. Okay, it's going direct in, outward all the time. And the line is a straight line. It's not, the vector field is not, doing the curly thing. It's not coming back. There's no circulation. It's only a flow of electric field outward. So curl of E is 0. This is the second equation of Maxwell equation. Okay, this is the second equation. So what do we have so far? We have number 1 here, divergence of E here, right? equal to rho divided by epsilon naught, this number 1 here and number 2 here, we have this. And this thing is actually very important. Since it's equal to 0, we can actually introduce another parameter. That parameter, okay, from this condition, condition, we can introduce what you call electrical potential. Okay, we can introduce electrical potential here. Okay, man. Okay, if this thing is true, okay, you can write E field here equal to gradient of some scalar function. Okay, it's scalar function. Any scalar function. Okay, if this thing is true, then we have this. Okay. Any questions? No? Anyone know that what else? What is the next step are we going to take? No? No one say anything. Okay. Let me show you this. Okay. Okay, we know that this curl E is equal to 0, right? And we know that from Stokes theorem. Curl E here dot dA here equal to the line integration of EDL here. All right. Okay, from here we can actually say that phi of R here is actually equal to minus E dot dl here. And the integration is from the reference. This thing is the reference. Let me use the reference. The reference point to where you want to find the potential. And anyone knows how this equation come from? From what I actually gave you. Can you tell me where it's from? No? Anyone? Come on, get involved in, in our lecture. So it's going to be more fun. And if you ask questions, if you, enjoy the class, it seems like you are just listening and, dying slowly. Can you tell me how does this equation come from? How that it comes? Okay. how are we going to derive it? How we end up with this equation from what we actually from this? No one. No, okay, you guys just quiet. Let me call your name. Metini, are you still there? Can you tell me how this equation alive? How are you going to derive it? มันมาได้ยังไงสมการเนี้ย
ค่ะอาจารย์
ครับสมการนี้มาได้ยังไงครับ
ไม่แน่ใจอะค่ะ
ที่คุณอะไรลองบอกสิว่าถูกไหมลองไม่แน่ใจก็บอกได้ บอกได้ครับ
มาจากสมการที่คูณกันด้านบนไหมคะอาจารย์ที่
สมการไหนครับ อันไหนเอ่ย มีใครจะช่วยเมทินีบ้าง
มาจากตัว
คือของ e
ค่ะ
ลองดูนะ ถ้าเราบอกมาจากเคอร์ของ e นะครับเคอร์ของ e เนี่ย e เราคือตัวนี้ถูกไหม
ค่ะ
curl of gradient is 0 is it เคอร์ของ gradient เป็น0ป่ะ
ค่ะ
มันก็ได้0ถูกไหมเพราะฉะนั้นด้านนี้เป็น0แล้วเกิดอะไรขึ้นต่อ
พอด้านนั้นเป็น0แล้วก็จะเหลือสมการด้านหลังอย่างเดียว
e dl เท่ากับ0
อันนั้นมาได้ไง
มาได้ไงเนาะ
อาจารย์
Okay, if let's come back to here, and if we know that before we do the cross loop, we can say that A and B is a different point. They are different, and we begin with this, right? It's not 0. Okay, now it's equal to what? It's equal to the integration of gradient Is this true? Is it true? And anyone can see where it come from now? And this thing here, let me write down here. I'm not going to worry about the limit of integration. Okay, let's do some really simple thing here. Okay, dl is what? You can put the whole thing in there, right? You can put the whole thing in here, but I only consider here dr because our E field is just, direct to r here. So it's doing this. What do we have? We have the integral of what? Okay, what's the result of this? Yeah. Is that clear? So what do we have here? So this thing is equal to phi here, right? So our phi is equal to what? Right, this thing has to be from A to B also, right? From A to B here. Any questions? Why are you guys so quiet? Come on. Okay, we have this thing here, phi B here, minus phi A here, equal to the integration A, B, E, dl. All right. Okay. Any questions? No, you guys don't have any questions. Now.
Teacher,
Yes.
I just wonder that the fundamental theorem of curl, right? Is it
Right.
it must be closed loop or not for the right part, the E dot
It has,
dl? Is
yes.
it
It has to be a closed loop.
oh, and A to B is also closed loop.
At this moment, I don't say that it's a closed loop. Okay, and I didn't get involved with this yet. I only use this equation
Oh,
here.
okay.
Okay.
Just the line.
Okay. So if this thing is what your friend actually say, I didn't say it. Okay. Actually, it's 0 if you have a closed loop, but I only consider this now. Okay. And I say that I'm not going to worry about the closed loop thing. I only do the line integral, the simplest form of it. And you just replace E with this. Okay. Oh, sorry, I forgot the negative sign here. I forgot the negative sign. Oh, okay. So this thing has to change the sign here. Sorry, I forgot the sign. Okay, when you do that, we have this. Okay. Now the important thing is the reference point here. What is the reference point? In general, this reference point is like when you are considering the reference point for a potential energy. You can choose any point as your reference. Remember when you study the potential energy, anytime you calculate the potential energy, you need to know where your reference point is, right? You have mg multiplied by the height h. You must know how you actually measure the height from where, right? Normally we measure it from the floor, right? Why we measure it from the floor? Because on the floor, the potential energy is 0. Because h is equal to 0, mg multiplied by 0. So you have 0 potential energy. So normally when we study the potential energy, we try to find the lowest possible, which is 0, as a reference point. Okay. So in this case, we want to know the reference point that actually give you the 0 electric potential. Okay, this has to give you the 0 electric potential. Which means that this thing is equal to 0. Okay, your reference point must be 0. Any questions? Okay, don't forget to put the negative sign here. I forgot it. Very sorry. Okay, so at point B here, okay, let me draw a picture here. At point B here, point A is here. Okay, point A is here. It's better this way. From here to here, we want to okay. At this point, at B, there's a chart. There's a potential electric potential phi B here, and at this point, they have an electric potential phi A here. To be able to find this electric potential, you need to find the reference point. Normally, the reference point is the point at infinity. Why we choose the infinity as our reference point? Because the potential is what? Can you tell me why we choose the infinity as our reference point? Why we choose infinity? Can you tell me? Because at infinity, the potential is 0. See, it's too far. If you think about electric field is equal to 1/4 pi epsilon naught Q divided by R squared. So the further you go, the lower your electric field. See? So if you want to have a 0 electric field, when you have 0 electric field, you have 0 phi. You have to go where? You have to go to infinity to get that 0. Is that clear?
Yes.
Okay. So from here, to be able to find this thing has to compare with what? With phi at infinity. This one also must compare with phi at infinity. Okay. So this thing you can say that is equal to integral of what? If you consider the first one is infinity to be EDL. Okay. Because we from infinity to B, from infinity to A, yeah, plus. Okay, A is here. So if we want to move back up here, this thing has to be negative here, infinity A. Okay, if you want to use the positive sign here, you have to do it like that. Okay, but we don't want that. We want this infinity to be, you know, at the lower limit. Okay, EDL here. This thing is, you can see here. Why are they different? Can you tell me why they're different?
Which one? This.
Okay, this one here. This one is phi B, right? This one is
Okay.
basically phi A here.
Yeah.
Okay. And you have a negative sign.
No.
Okay, this one is what? This one is phi B. This one is phi A here. Something wrong here?
Yeah, I think you forgot the. Did you forget or you just is it truly different or you forgot the side?
Sorry, I forgot what?
Minus side or it is different? I am not sure.
Oh, right. Sorry, hold on, let me check. I forgot the minus sign.
Yeah. In
Anyone know where I forgot the minus sign here? Did I forget the minus sign? Did I? Maybe I did. And I actually write this thing wrong also. It has to be minus here. It has to be minus here and plus here,
yes.
right? Okay, so it's minus psi B plus here. But is this what we want? Okay, from here, let me write it up here. Let me write here. It's a little bit too dense there. Okay, let me write here. Minus infinity to, to B, right? EDL. And you have plus. Right, this thing is equal to A to B, DL. All right. Okay, so now it's correct. Okay, but from here, if you look, A is up here, B is up here, right? We want A and B just to follow this thing here. I should not convert this, actually. I should not convert this. I should use it the same thing. Okay, this thing is infinity to B here, EL. Okay, I don't know why I converted. Okay, okay, EL. So by using this, we know that the whole thing is just the integral from A to B here, E dot dl. Okay. So which is what? Phi B minus phi A. Okay, any questions มีคำถามไหมตรงนี้ถามได้นะไม่งงนะครับ Anyone understand why this thing here is equal to here, equal to this one, equal to this expression? A to B here, B is up here, A is down here, and we have the same infinity. So the result of the infinity will subtract each other, they will cancel each other out. So we don't have it here. We only have the potential at B and the potential at A. Any questions? Okay. No, everyone understand it. I hope. Okay, now let me write it down again so that you can see it clearly. We have phi B here minus phi A here. อันนี้คือความต่างศักย์ระหว่างจุด A กับจุด B โอเคไหม equal to what? Okay. Oh, sorry. I thought that I go up all the way here. Okay, this is the potential difference. ดูภาษาไทยด้วยว่าความต่างศักย์ Okay, equal to the minus integration from A to B here. E dot dl. Okay. And this one here is the different, the potential different, or you can say it's like that. Okay. Delta potential. And we know that from the fundamental theorem of gradient. Remember, what does this theorem tell us? It tells us that anything, let's say if previously we used TB log TA, right? Any scalar function, you can write it like this. Remember, this is the fundamental theorem of gradient. This thing is delta T. T can be any scalar function. So in this case, our phi is a scalar function, and it's actually show the form similar to this one. It has the form similar to this one. So phi B minus phi A here is equal to what? Equal to the integral from A to B. Gradient phi. Yeah. Any questions? I just put like this. See? I didn't do anything weird, right? No questions. Okay. Anytime I pause, I'm looking for questions, but Normally when I pause, you just quiet. Okay. Now we know this thing is equal to this one here. And okay, I only do this, A to B here, dl here, equal to minus E dot dl here. Okay. To have this expression equal to each other, to have this equal to this one here, our E and our phi here. Okay, this the derivation. So this is our result. So this concept is true here. Phi r here is equal to the integral from any reference to r here, E dot dl. So this expression is true because it gives the same result here.
Teacher,
Yes.
the fundamental theorem of gradient. Do we have delta t?
Yeah, this is equal to delta t here. It's not divided by delta t.
Oh, okay. Oh, sorry.
Okay. Okay. I should not like it like that. So it's equal to delta t here. Okay. Okay. Again, correct. So now we can conclude that E equal to minus gradient of V of potential, electric potential. But this thing has to come from this. Okay. If this thing is not true, if not, if it's false, E not equal to, okay, it must be true, so that this thing will be equal to the gradient of the potential function. Okay. Any question? No questions. Okay. Now let's check. Let's do an example. Example always fun to do. Okay. We have a sphere. Okay, the simplest form. We have the sphere of radius r, and we have point r here that we are interested. Okay. Now we want to find the potential, electric potential. We want to find the electric potential inside and outside of this sphere. Okay. Okay. And this sphere have a surface charge. Okay. The surface charge of this sphere is sigma, the same thing. And uniform. Okay, so it's distributed evenly on the surface of this sphere. Okay, it's a shell. We only consider the shell here. It's not a solid sphere, it's the shell sphere, spherical shell. Okay. So what are we going to do here? So we know that from Gauss law, right? From Gauss law. We can find E field inside by creating a Gauss surface inside, and we can find E field outside by creating a Gauss surface outside. We can do both. And we know that if we create this Gauss surface here, Gaussian surface, okay, for R outside the sphere, the shell here, and this one is the Gauss surface for R for the inside, okay. Now, let's check for the inside first. It's simple for the inside, this one here. This Gauss surface, does it cover the charge? Does it? ถ้ายังจำได้เนาะ Gauss surface เนี่ยมันจะต้องคุมประจุใช่ไหมอันนี้มันคุมประจุไหมประจุอยู่ตรงนี้อยู่บนผิวไม่มีข้างใน Gauss surface สำหรับ inside มีไหม Is there a charge inside this surface here มีไหมมันมีประจุไหม Is there a charge No there's no charge inside the sphere in here no charge when there's no charge E field is what 0 inside Is it clear So E field inside the sphere, the shell here, we can use the spherical shell. Is 0. Any questions? How about the potential? Is it 0 inside the sphere? Look here, E here, equal to minus gradient of phi. To get E 0, what is the value of electric potential? Is it 0 also? มันเป็น0ด้วยไหมเพื่อที่จะให้ E เป็น0เนี่ยไอตัวศักดิ์ตรงนี้ต้องเป็น0ด้วยไหมจำเป็นไหม Is it necessary to be 0?
Constant.
Yeah, it can be a constant. It doesn't need to be 0. But normally we choose it to be 0 because it's a constant. It can be any number. Okay. Okay, it can be any number. And actually it depends on the field outside the sphere. Okay, now let's consider outside the sphere. So outside the sphere, E field is what? E field is equal to 1 over 4 pi epsilon naught, right? Q here, let's say the overall charge is Q, okay? Okay. To find the potential, okay, at R here is equal to, from any reference until R here, EDL. Okay. Let's set our reference to be infinity. Okay, now I'm going to replace all the reference with infinity. Okay, so let's say Okay, 1 over 4 pi epsilon naught q divided by r palm. Okay, dr palm. R palm square here. Forgot square. Okay, what do we have here? We have find r here equal to 1 over 4 pi epsilon naught q divided by r palm from infinity to r. Okay, the reason that I don't use normal r here because our reference, okay, it's not infinity here, it's r here. It's r here. I don't want to use the same variables. Okay, I just use any dummy variables here. Any questions? No. Okay. Okay, do we have this q here? Since 1 over r here minus 1 over infinity, this thing is basically 0. So our find here equal to 1 over 4 pi epsilon naught q over r. Okay, this is the potential of this sphere where r is greater than the radius of the sphere. Any questions? Okay, now we will come to see this thing is outside. We forgot to write outside. Now we want to find the potential inside. We know that it's a constant. It can be 0, it can be anything. Okay, let's check it. How actually I tell you that it actually depends on the field outside. Now, what I just said before that it can be anything 0 or anything. Maybe it's not correct anymore because it depends on the charge outside. Okay, but it's surely constant. It's a constant. It must be a constant, but it cannot be anything. It has to be something that depends on the potential outside. Okay, now let's consider this. So now we want to find the potential inside. Okay, inside where r is actually less than r, yeah, the capital R here. Okay, now let's think about this. Okay, we have a sphere. Okay, and we want to find the potential inside the sphere, let's say at this radius. Okay, our reference point is at infinity. Okay, this is the reference point. So first we have to do this integration until the surface here are here. To the surface, we have to find the potential from the surface, and from the surface here, go inside. Okay. Why do I have to do this? Because normally when we want to find the potential inside, let's say the radius here is anywhere, right? This one is r, right? Let's see r palm here. So we want to find the potential inside where is r palm here. So we want to compare this to find at infinity, right? We have to compare, we have to reference this point to the infinity. So to get this, we have to do this integration. Okay, from infinity to the surface here. And we have q divided by r palm square is 1 over 4 pi epsilon naught dr. Okay, from minus infinity to the surface here. And from the surface go inside. And the electric field inside is 0 here, right? So electric field inside is 0, so we don't have to worry about the electric field here. Okay, forgot the minus sign here. Okay, normally I should write down something like this. Right, and from minus infinity to r palm. Okay, let's like it as r instead. So r here, and this one is r. It's easier, so I don't have to use double palm here. Okay, any question? From positive to r palm here. So we want to find from the potential from the infinity to r here, and from the surface to here. So this is the actual integral. And this one actually can split into two integral. It's minus from minus infinity to r here, and e outside dl. And what minus from r to r inside, e inside dl. Okay. And e inside is 0, so you have this. E outside is this one. Is it clear? So what is our potential? It's only this term here, and which we did it already, right? It's become 1/4 pi epsilon q divided by r palm here, from infinity to r. And we have 1/4 pi epsilon naught q 1/r minus 1/infinity. And this one actually 0. So phi outside, no, not outside, sorry, it's inside, equal to 1/4 pi epsilon naught q divided by r here, where r must be less than r. This is what happened inside. Okay, any questions?
Teacher,
Yes.
I don't understand much.
What?
I
Can you say that
don't-
again?
I don't understand much. Can you explain the step again, please, from the potential outside?
From the beginning.
Maybe.
Okay. Okay, let's start it over. Okay, we have a sphere, right? And this sphere is having a radius of r. Okay, and have a surface charge of sigma here. And the surface area is A. So sigma multiplied by A is equal to Q. Right? Now we want to find the potential. Okay, inside and potential outside. Okay, we want to know how much it is. Okay, let's first find the potential outside. Okay, it's equal minus, let's say from infinity, this is a reference point, until r here. R can be anything, but r here must be greater than r. Okay, this E out, dl here. Okay, since our E, we can find it using Gauss surface, right? Gaussian surface. Let's say we draw Gaussian surface. Our E is what? Our E just equal to 1/4 pi epsilon naught Q divided by R squared. Okay, and vector is this one here, divided dot with the dr here and r here, and the rest theta multiply plus fine. This term is 0 because there's only radius dependent direction. So phi and this thing doesn't exist. So phi outside equal to this. No, it's not negative here. Why I put negative sign here? Okay. 1/, okay, here, here. All right. And we can do the integration. I'm not gonna do it. It's your job to try the integration. It's just mathematics. Okay, where R must be greater than R. Okay, this is outside. Equal to 1/4 pi epsilon naught Q divided by R. Okay, it is outside. Any questions for the outside?
Is can you draw the small r in the picture?
It's the radius of your Gaussian surface. If you want to find the electric field here, you draw Gaussian surface that touch your. If you want to find here, you have to draw Gaussian surface like this. If you want to find here, you just draw it bigger. Okay. If you want to find here, just draw it bigger. It depends on where you want to find. It can be any R.
It can also be inside for the potential inside too, right?
Yeah. But the potential inside, but the electric field inside is 0. Okay. Now we come back to the potential inside. Okay. It depends on R also. Equal to what? Minus, not minus infinity, is infinity. Why I keep saying minus? Okay, it's minus here. And to R here. But this R must be inside. Okay, this R has to be inside. Can be any R here. Or let me draw another circle. Okay. Now, our R is somewhere here. Okay, now we want to find the potential inside. Okay, this R here is minus, still the same thing here. E here, dl. I didn't write down E, the electric field inside or outside. Why do I do that? Why I just put in here like that? Can we do that? No, we cannot do that because our integration is coming from infinity. Okay, it's coming from infinity. So we cannot just use E inside because from infinity coming inside, it has to go through what? This one first. Okay, it has to go through this one first and then inside. So there are two steps here. This is the first step here, from infinity to R here. And the other step is from R here on the surface here, coming inside. Okay, there are two steps. so our integration, this thing is just the definition นี่คือนิยามเราหนีมันไม่พ้นเห็นไหม we begin our calculation with the definition and from here we can split เราสามารถแยก we can split the integral into two parts. The first part is from infinity to the surface of the sphere. Okay, this from the infinity to the surface of the sphere, right? So this thing we can call E out dot dl because outside the electric field is E out, and we actually know what it is, right? It's just this one. Okay, this thing is E out. And what next? From R surface to the point R inside, and it's E inside. Now it's we are this integral show that we are inside the sphere. Okay, and luckily we know that this E here, we don't have it. We don't have the electric field inside, so this term is 0. It's 0 because E inside is 0, but we still have this term to take care of. Okay, therefore phi inside okay, which is equal to this. Okay, I'm not going to do the integration for you. Okay, any question? Is it clear? Any questions? No? Okay, if you don't have a question, you probably ready to do homework. Yeah. Okay, 2.21. Now I will know that you understand it or you do not understand it. Okay, and 2.23. Only 2 of them. Any question? No? Okay, good. So you guys, no question, understand everything perfectly. Now we come to possibly the last part of this electric field thing. Okay. After this topic here, we will study the boundary condition เงื่อนไขขอบเขต and the energy of the electric field, because we know now we can calculate the force, Coulomb force. We can calculate the electric field, and we know that all this, when we have force, we have work, we have energy, and we haven't talked about energy yet, so we will come to energy later. Now we are still at the end of the electric field here. Okay, the topic here will be the Poisson equation and Laplace equation. Okay, these two very important concept here. We know that E is equal to minus sign here, and we also know that the first equation of Maxwell equation, right? Rho divided by epsilon naught. And we also have, okay, now we have 3 generals เรามี3ขุนพลอยู่นะครับ we have three equations that is very important. Okay, Now, what we are going to do here is that we want to know that how are these three equations be written in the form of this and this. Okay. Okay, let me write down this. Okay, from here, let me draw this thing is number 1 here, this thing is number 2, this thing is number 3. Okay, from number 2, divergence of E is equal to rho by epsilon naught. So we want to write down this equation in terms of potential. How can we do that? We use number 1 here. We change all the electric field into potential. We have this. All right. And we know that what is this thing here? All right. Is it easy? It's really easy. So now we can write down this equation in terms of potential like this. This term here is called Poisson equation. Okay, this thing is Poisson equation. Okay, Poisson equation. How about Laplace equation? Sorry, it's going to keep stretching. How about Laplace equation? Laplace equation is Poisson equation in free space. When you see the charge density is 0, it means that in that space there is no charge. So it's a free space. There is nothing in that space. So Poisson equation will turn to Laplace equation when rho is equal to 0. That means this thing here. This thing is Laplace equation. Okay, this thing is Laplace equation. Okay. And now we did this with number 2 here. We write down this equation in terms of potential. Now we write down the equation number 3 in terms of potential. From number 3 here, we know that curl E is 0. So we replace E with this curl of gradient phi here equal to 0. Okay. And this thing show nothing because curl of gradient is always 0. We cannot do anything more than this. Okay. This thing we cannot go anymore any further. We can only say that from here E can be written as this thing. That's all. We cannot do anything more. All right. Okay. Now, so far we have we actually finished this electric field here, and now we have to end this topic with the potential, because when we so far we have studied the potential, the electric potential for charges, for for a single charge, a point charge, for point charge. But normally we don't have a point charge, we have a charge distribution. So what are we going to study next is we're going to learn the potential, the electric potential, the electric potential of a localized charge distribution. Okay, now we will see what happens if our charge is no longer a point charge. It's some kind of, has a dimension. Okay. Okay. Now let's think about it first. Let's say we have a space and we have a point Q here. Okay, we have a point charge Q here, and we want to know the potential here. And we know this. This thing is R. Okay. Then our potential is what? Okay. Potential is not vector, so you don't have to worry about the vector nature. All right. And if we have another charge coming here, and another charge here, and another charge here, and another charge here, another charge here, we have so many charges. So what is the potential? The potential is the, well, okay, we can have this, we can have this, we can have this, we can have this. You can say that this one is R1, this one is R2, this one is R3, this one is R4, this one is R5. We have so many R here. So, and we have Q1 here, Q1 here, this one is Q2, this one is Q3, this one is Q4, this one is Q5. You can have many Qs also, many charges, discrete charges. Okay, so the phi total is equal 1/4 pi epsilon naught and summation I, right? To, well, let's say you have so many of them. Let's say n qi divided by ri. This is the total potential ศักย์รวมทั้งหมดที่เกิดจากประจุเหล่านี้ Okay. How about we have an object with some dimension. We want to find the potential at this point, again, point P. Okay, how can we do it? So we have to choose a very small portion, right? And how this portion affect this point. Okay, this one is R. And how can this point affect this? Okay, we have too many of them, so we do have to do the integration. So here the potential R here equal to 1/4 pi epsilon naught, the integral, okay, of 1/r dq, because this point here is dq here. So we have to do the integration for the whole volume of this object. All right. And we know that if we have a three-dimensional object here, the charge density dq here divided by dv equal to rho here. Okay. All right. This thing is v prime here. So our potential is equal to 1/4 pi epsilon naught with the integration. Okay, this thing is the potential of a charge distribution is for the volume charge here. Okay, it can use to calculate the electric potential. Okay, any question? Or you can say that this thing actually, remember we have a Poisson equation. This thing you can consider it as a solution to Poisson equation. Okay, when you have a charge in the space. Okay, now if we recall that the electric field here, remember electric field here, R here equal 1/4 pi epsilon naught, the integral rho R here divided by R squared R here dv palm, right? If you remember this, we know that we have E field, this is for volume charge. We have a surface charge. Okay, I'm not going to write down E field for the surface charge. I'm going to write down phi, the potential for the surface charge is equal to 1/4 pi epsilon naught here, the integral from lambda. This thing is not a surface charge, it's a line charge. Okay. For the surface charge. Okay, this is for the surface charge. So we have everything for line charge, surface charge, volume charge. We have everything. Okay, now we're going to finish this class with an example. Okay. So we have a spherical shell again. Okay, spherical shell. This example is similar to the previous one. Okay, we want to find the potential of uniformly charged distribution. This thing is sigma. Okay, and its radius is r. The result of this example should be identical to the previous example. Okay, should be identical to the previous example, but we just use different concept. Okay, now we're going to use this. We are not going to use phi equal to previously in the last example. We use this relation. We use the definition of potential, right? We know that the potential here minus equal to EDL. Okay, we use this previously. Now we're not going to use this. We're going to use this. And it should give you the same solution, the same result. If you have different result, it means something is wrong. Whether you did this one incorrect or correct, and you did this one incorrect. Okay, they must be equal. So let's try to use it. Okay. Okay, 1/4 pi epsilon naught here, the integral from sigma divided by r dA palm. Okay, our sigma is constant, so we don't have to worry about it. So we just pull it out. Okay, what do we have here? We have 1/r here, dA. Okay, since we only consider at the surface here, this thing can be dA here. All right. And our dA is what? And this thing is radius r here. Our dA is equal to what? R square, right? Sine theta, d theta, d phi. All right. How about our R here? So we know our A here is equal to this one. How about R, the separation vector? This has to be very careful. Now you have to be very careful. Okay, let's draw a reference frame here. You should draw it every time. Okay. We have a it's a really bad circle. Okay. All right. So this is the point where we interested in. Okay. And the point where we want to find the potential is this point. So we have a effect of this on here. Okay, the height here from this thing is x, this thing is z, this thing is y in here, this thing is x here. So the height, the distance here, let's say, let's give it z. All right, and this angle is what? Phi prime here. Okay, and this is the distance, the separation vector. All right, so our R here is what? Is R minus R prime, right? R is the location of the observer. Okay, so our observer is CK. Okay, and our source, our charge is here. Is here. So our charge is what? Oh, sorry. Because we are doing it's only the size. We don't have to worry about it. Actually, we know this. Oh, sorry. I was into vector too much. Sorry. Okay, we want to find this distance here. Can we calculate that? We want to find this. Okay, we don't need to use this at all here. We don't need to use it. We can use the cosine law here. We know the angle, this one. Okay, and we want to find the size of R here, and it's equal to what? This thing is R, right? We R squared plus C squared minus 2 C cosine theta prime. Any questions? Any questions? And we have to, okay, are you guys still there? Let's stop here. I think you guys are out of your body now. We can continue this later. Okay, let's call it a day. All right. Any questions? Anyone still there? No answer?
Yes.
I'm here, teacher.
Okay. Do you guys understand everything? Or just how many percentage do you understand? Like 70, 60, 50? No,
I understand.
most of it, right? วันนี้เราทำอะไรไปบ้างอ่ะ ตอนนี้เรา คำนวณหลักๆก็ potential เนาะก็คือหาศักย์ไฟฟ้านะครับศักย์ไฟฟ้าที่เราหาตอนแรกก็คือศักย์ไฟฟ้าที่เกิดจากประจุเนาะเรานิยามศักย์ไฟฟ้าแล้วเราก็พิสูจน์ว่า E เนี่ยสนามไฟฟ้าเนี่ยเท่ากับเกรเดียนลบเกรเดียนของศักย์ไฟฟ้าเนาะทำไมเราต้องมานั่งพิจารณาศักย์ไฟฟ้าศักย์ไฟฟ้าเนี่ยมันสำคัญตรงที่ว่ามันไม่ใช่เวกเตอร์นะครับมันไม่ใช่เวกเตอร์ถ้ายังจำได้ตอนที่เราทำหาสนามไฟฟ้าเนี่ยนิยามของสนามไฟฟ้าเนี่ยเราต้องไปนั่งกังวลกับเวกเตอร์อยู่ใช่ไหมเหมือนเมื่อกี้ที่ผมทำตอนสุดท้ายอ่ะแล้วผมไปยุ่งกับเวกเตอร์ผมลืมไปว่าเราทำกับสนามไฟฟ้าเราไม่ต้องไปกังวลเรื่องเวกเตอร์ผมก็ดันไปทำเป็นเวกเตอร์ซึ่งจริงๆแล้วสำหรับศักย์ไฟฟ้าเนี่ยมันง่ายกว่าที่จะเป็นในการคิดมากกว่าที่เป็นเวกเตอร์เพราะถ้าเป็นเวกเตอร์ปุ๊บคุณต้องคิด3เทอมก็คือ x เทอม y เทอม z ในกรณีที่เป็นพิกัดฉากถ้าเป็นพิกัดทรงกลมคุณต้องคิด r เทต้า phi ใช่ไหมแต่พอเป็น potential ปุ๊บคุณไม่ต้องไปคิดอะไรเลยครับไม่มีเวกเตอร์มันมีอยู่แค่เทอมเดียวก็เทอมนั้นแหละนั่นคือข้อดีของศักย์ไฟฟ้านะครับเพราะฉะนั้นเวลาเขาจะหาสนามไฟฟ้าเนี่ยเขาพยายามไม่ไปยุ่งกับนิยามของสนามไฟฟ้าว่าหายังไงเขาพยายามจะหาศักย์ก่อนพอหาศักย์ได้ปุ๊บเรารู้ว่าสนามไฟฟ้าเท่ากับลบเกรเดียนของศักย์ไฟฟ้าเราก็เอาเกรเดียนไปออเปเรตลงบนศักย์ไฟฟ้าเราก็จะได้สนามไฟฟ้าออกมาพอจะเห็นภาพไหมนั่นคือสาเหตุที่เราจะต้องเรียนศักย์ไฟฟ้านะครับแล้วศักย์ไฟฟ้าเนี่ยเนาะที่เราเรียนตอนแรกก็คือเป็นของประจุนะเป็นจุดประจุนะจุดประจุแต่ละอันเนี่ยก็จะมีศักย์ไฟฟ้าเป็นของมันเองนะครับแต่เราสามารถหาศักย์รวมได้นะศักย์รวมก็คืออะไรครับก็เอาศักย์ของแต่ละอันมารวมกันเนื่องจากว่ามันเป็นสเกลาร์เห็นไหมมันง่ายมากเลยมันแค่เอามาบวกกันเฉยๆไม่ต้องไปสนใจว่ามันทิศไหนบวกกันปุ๊บนั่นคือศักย์รวมเสร็จแล้วเราก็มาหา distribution นะฉากที่ไม่ได้เป็นจุดประจุที่มันเป็นขนาดมีมิติอยู่นะครับเราก็อินทิเกรตมัน